Earth's layers and moving plates. The big question: how do tectonic plates and Earth's layers interact to change the surface of the Earth? Alfred Wegener's continental drift hypothesis explained many of the why questions. It explained why the edges of some continents fit together like puzzle pieces. It explained why continents separated by vast oceans have similar types of rock formations and fossils. What the hypothesis couldn't explain was how. How could a mass of solid rock as large as Asia or North America move thousands of miles across Earth's surface? It would take an enormously powerful force to do that. Geologists in Wegener's day didn't know of any force on Earth's surface powerful enough to move continents. As a result, most geologists rejected the idea of continental drift. For decades, Wegener's hypothesis was harshly criticized. Still, a few geologists thought Wegener was on the right track. What if the driving force behind continental drift was below Earth's surface? How can you discover what lies beneath Earth's crust? Oddly enough, earthquakes helped scientists answer these questions. What waves reveal? Have you ever tossed a small rock into a pond? Little waves travel out from the spot where the rock hits the water's surface. Although you can't see them, waves travel through the water below the surface too. An earthquake is a bit like a rock plunking into water. During an earthquake, the ground shakes. The shaking is caused by waves of energy traveling out from the earthquake's source through the earth. Scientists call these seismic waves. Powerful seismic waves can travel very long distances. They can travel through Earth's crust and deep into its interior. Around the time Alfred Wegener was thinking about continental drift, scientists were studying Earth's interior using seismic waves. How? Using instruments called seismographs. They tracked seismic waves traveling through the planet. Seismic waves move in slightly different ways as they move through different materials. For instance, they travel faster through solids than liquids. Studying seismic waves helped scientists identify Earth's four main layers. Earth's deepest layer is a solid inner core of very hot metal. This metal may be nearly as hot as the sun's surface. The next layer, the outer core, is also made of hot metal, but it's liquid, not solid. The mantle surrounds the outer core. The mantle is Earth's largest and thickest layer and consists of very hot, very dense rock. The rock is solid in the lower and upper parts of the mantle. In between, however, is a region where the rock is neither liquid nor solid. The slow movement and behavior of this material caused by heat and pressure have an impact on Earth's surface. Above the mantle is Earth's outermost layer, the thin, rocky crust. There are two types of crust: oceanic crust and continental crust. Oceanic crust is covered by ocean water. Most of the continental crust is dry land, but some of the crust around the edges is covered by water. Oceanic crust is thinner but heavier than continental crust. For scientists interested in continental drift, it was the slowly moving material in the middle of the mantle that caught their attention. Did material movement in the mantle contribute to crust movement too? Could this be part of the reason why continents drift? Some scientists thought so. Before they could be sure, however, they needed evidence the Earth's crust was actually moving. Clues from the seafloor. During the 1940s and 1950s, new technology enabled scientists to make detailed maps of the seafloor. The maps revealed long chains of underwater mountains, called mid-ocean ridges, in all of Earth's oceans. There was a split, or rift, that ran down the center of these ridges. The rift was like a seam in a pants leg where two pieces of fabric come together. Scientists dredged up rock samples from mid-ocean ridges. All the rocks were basalt. Mid-ocean ridges seemed to be like long, skinny strings of volcanoes running along the seafloor. Scientists collected rocks at various distances from the rift along a mid-ocean ridge. They discovered that rocks from the edge of the rift had formed very recently. Rocks farther away from the rift were older. The farther scientists got from the rift on either side, the older the rocks were. The scientists concluded that mid-ocean ridges form along huge cracks in Earth's crust. Magma beneath the crust erupts through these cracks as lava. The lava cools into basalt, creating new oceanic crust on either side of the rift. As new crust is added, older crust gets pushed outward, away from the rift. Inch by inch, year after year, oceanic crust spreads outward into ocean basins on either side of mid-ocean ridges. Scientists called this process seafloor spreading. They theorized that as the seafloor slowly spreads, continents bordering the ocean slowly move apart. Here was one explanation of how continents could drift. Scientists knew the Earth wasn't getting bigger. If new crust forms along mid-ocean ridges, then old crust must be destroyed somewhere else. Scientists guessed that deep ocean trenches are places where crust is sinking down into the mantle. In the 1960s, scientists formed a new theory about how Earth's surface changes. They called the theory plate tectonics. Moving plates. Scientists are still learning about plate tectonics. The theory of plate tectonics states that Earth's crust, together with the solid top of the mantle, is broken up into sections. These huge rocky slabs are called tectonic plates. Tectonic plates fit tightly together. They aren't fixed in place, though. They can move. They move because of heat and pressure in the mantle. As the material in the mantle slowly moves, it exerts enormous pressure on the overlying plates. All that pressure forces the plates to move as well, very, very slowly. Earth's tectonic plates have been slowly moving and interacting for billions of years. They interact mostly along their edges or boundaries. Plate boundaries are where two or more tectonic plates meet. A matter of time. At some boundaries, tectonic plates are moving apart. As the plates separate, molten rock flows up from the mantle into the space between them, creating a new crust. Mid-ocean ridges are an example of this type of plate interaction. Tectonic plates along the mid-ocean ridge in the Atlantic Ocean are moving apart at a rate of about 0.8 to 2 inches per year. That may not seem like much, but it adds up. 200 million years ago, the landmasses of North America and Europe were joined. So were South America and Africa. Thanks to separating plates, these continents now lie on opposite sides of a vast ocean. At other plate boundaries, tectonic plates are colliding or crashing together. In some places, colliding plates slowly crash into each other. The crust at their edges gradually crumples and is pushed higher and higher, creating mountains. In other places, one of the colliding plates slides under the other. Two plates are colliding this way along the western coast of South America. A heavier oceanic plate is sliding under a lighter continental plate. Scientists call this process subduction. Subduction has created a deep ocean trench off the coast of Chile and Peru. It has also had a role in creating the towering Andes Mountains along the western edge of South America. Similar plate interactions have formed mountain ranges throughout Earth's long history. Finally, tectonic plates slide sideways past one another. It's never a smooth process. Plate edges press together hard. They often get stuck while the pressure keeps building. Eventually, the pressure gets too great. The stuck edges break free, causing the plates to jerk past each other. Providing the answers. The theory of plate tectonics answered many questions in geology. It explained how Wegener's Pangaea broke apart. It explained how the continents have been slowly rearranged over millions of years. The movement of the plates also explained mid-ocean ridges, deep ocean trenches, patterns in the location of mountains, and many other features on Earth's surface. The theory has become the cornerstone of modern geology. As plates move, interesting things happen. Most of the time, they happen incredibly slowly. Sometimes, though, the effects of plate movements are sudden and dramatic. Think earthquakes and volcanoes. Core conclusions. You may never have heard of Danish scientist Inge Lehmann. Among seismologists, however, she is famous. Around 1900, scientists thought the Earth had just 3 layers: an outer crust, a solid mantle, and a liquid core. Lehmann studied seismograph records of earthquakes. She analyzed how seismic waves changed as they traveled through Earth's interior. Lehmann collected thousands of records organized in boxes. There were no computers back then. She saw patterns in how seismic waves behaved as they moved through Earth. Lehmann concluded that Earth's core has 2 parts: a liquid outer core and a solid inner core. In 1936, she announced her findings and changed our view of Earth.